And of course, for today, we're focusing on agriculture and the role of nanotechnology with special emphasis on fertilizers. But among the agricultural applications, you could have fertilizers, you could have pesticides, you could have sensors for biodetection, and you could have applications in environmental and soil remediation. So for today, I'll be focusing more on the fertilizers. So some general properties of nanoscale materials. As you may already know, they are small in size and they range between 1 and 100 nanometer. Therefore, they are submicroscopic. So they can be 10 to 1,000 times smaller than a bacterium. And for that reason, we can't see them with our naked eyes. The box here shows how the surface area can be impacted. So you can move from surface area of 96 centimeters square to double that if you just reduce the size of the material from one size to smaller sizes. And due to that effect of small size, they are highly reactive, and because they are reactive, they respond very rapidly to environmental cues, which go on to determine their fate. And such cues include such fates include aggregation, dissolution, and surface modification. So what is the product of nanotechnology? Basically, nanomaterial or nanoparticles. The difference between nanomaterials and nanoparticles is obscure, but I can say that all nanoparticles are nanomaterials, but not all nanomaterials are nanoparticles. The important thing is that they have a dimension that is of the nanoscale. We can also have products that are nano-enabled, which are not pure nanomaterials per se, but bulk materials that are infused or incorporated with nanomaterials. Like you see here, these are a cartoon for nanomaterials. You take this material, you infuse into the bulk material, either on the surface or on the inside. So whatever method, this material will now be referred to as a bulk, as a nano-enabled bulk material. There are hundreds of products that are nano-enabled, and one of them is nanofertilizers, which is simply fertilizers that exist as nanoscale or that contain nanoscale materials in them. So why do we need nanofertilizers? Well, we know that mineral fertilizers such as nitrogen and phosphorus and potassium feed half of the global population. And these mineral fertilizers they are characterized by poor nutrients use efficiency. So how plants use them is very low, less than 30% of, if you apply any amount of nutrients, the plant only uses about 30% of it. So that's quite low. On top of that, climate change effects affect the resiliency of our production systems. And this is worse in places like Africa and other tropical regions due to the environment. Climate change events, which includes drought, insect, and plant disease prevalence, they affect how plants use nutrients. So, which again adds to the issue of low use efficiency. And it's appearing increasingly ensure that nanotechnology can enhance nutrient use efficiency and can allow for minimizing input of mineral fertilizers into the biosphere. So what more can we ask for if we can have a system that allows us to do all of this, increase our yield by using lower rates? So the key goals of nanofertilizer, of course, the first thing will be to increase yield, and it's likely we can do so with less nutrient input into the biosphere. You see here this graph here. This is the control with no nanofertilizer, just with the normal NPK. When you add nitrogen, urea coated with zinc, you see the increase, and the zinc is used at 1%. 1% zinc is used on the urea for coating. And this is the bulk, the normal zinc that farmers use. You coat it with 2%, you get the same yield. So you can increase yield compared to the control, but compared to the bulk, you can use less. So you can increase yield and use less without no sacrifice. Same goes for the nutrient uptake. The same scenario here, zinc uptake in the plant, greater with the zinc nano and bulk compared to the control. But between the bulk and the nano, whereas the nano is 1% and the bulk is 2%, you get the same response. So you increase yield using less nutrients. Another goal will be to reduce nutrient loss, example through leaching and volatilization when compared to conventional fertilizers. Here you see this graph here, this line here shows the conventional phosphorus fertilizer. You see how much phosphorus is leached from the soil over time. But these graphs here are some of the nanomaterials and the control, no phosphorus. So you see how low it is. So by using a nanofertilizer, you can reduce the losses coming from using phosphorus fertilizers. So how do we synthesize some of these nanoparticles for fertilizers? So we can do so by several means. We can do so by physically milling the bulk materials, example, phosphate rock, into nanoparticles. We can use chemical means, such as using reductants, example, glucose or sodium borohydride, and precipitants, such as sodium hydroxide, to reduce and precipitate the salts into elemental particles. Example again, ammonium nitrate. We can synthesize nanoparticles using biological means, which implies use of plant or microbial extracts that contains enzymes and natural reductants to reduce dissolved salts into nanoparticles. And again, an example would be ammonium nitrate. And lastly, we can do what they call aerosolization. I'm not so familiar with this, but it involves the atomization of suspended bark particles into dry nanoaerosols. So to produce this image here shows just producing of nano-scale nitrogen from conventional sources. So this involves basic wet chemistry between urea and hydroxyapatite, whereby you dissolve your urea in water and then you add some calcium hydroxide solution. You mix mix the solution for a period of time. You add your phosphoric acid dropwise, and that forms the urea hydroxyapatite in a ratio of 6:1. You stir this under some condition, example for 2 hours. You dry at some temperature, and you get your products. What you see here is the crystals of the urea hydroxyapatite nanohybrid. And when these fellows here tested this for solubility compared to the urea, you see that over time, the normal urea that farmers use dissolve immediately. Immediately you add in water or put in soil, it dissolves, and then it plateaus out. The nano urea keeps dissolving slowly but steadily over time. So by doing this, you are controlling the release of the nitrogen from the urea that is nano-enabled compared to the plain urea. So this will be an advantage in terms of how you manage your nitrogen in the soil. So this slide shows producing nano-enabled nitrogen from another example of producing nitrogen from conventional sources using nanotechnology. Again, it's a wet chemistry process involving urea and nano-urease inhibitor. So what these people did here was they took a clay called atapogite. There is a lot of atapogite in Africa, especially in South Africa. So atapogite is made up of magnesium, aluminum, and silicate, and it's a nano clay. So you take this material, you add it to a polyacrylamide gel. It causes flocculation, which is what you see here. These are the crystals. Now it flocculates, and in that mixture, you add sodium humate. Sodium humate is supposed to be a natural urease inhibitor. So urease inhibitor, I will talk about it shortly here. Then after adding the sodium humate, you add the urea itself. So you form a composite of atapogite, acrylamide, sodium humate, and urea. And when you characterize this material for hydrolysis of the urea to ammonia, you see that the red one is the product and the blue one is the plain urea. You see that the plain urea hydrolyzes faster than the product. So, and this means you are losing your nitrogen with higher hydrolysis, and you are saving your nitrogen with lower hydrolysis. And as you increase the amount of urease, which is the enzyme that converts urea into ammonium, you see how the effect of the product takes place compared to the plain urea. Again, with time, the same scenario here. The urease, the urea alone with no enzyme, of course, you expect that to be low. When you have the product, lower hydrolysis occurs, and when you have just the urease alone with urea, of course, you expect that to be high because the enzyme is degrading the urea into ammonia. So this is the mechanism here. Under normal condition, urea is hydrolyzed to ammonium with loss of ammonia, and the ammonium is nitrified to nitrate. with loss of nitrous oxide, which is the so-called greenhouse gas that we all talk about. So this is a straight process that causes a lot of losses in the nitrogen. There's loss here as ammonia, there's loss as nitrous oxide, and there's loss as nitrate that leaches. If you add your urease inhibitor, in this case will be this product here, the red product. What you see here is that it blocks the rate of hydrolysis so that less ammonia is lost. Therefore, less nitrification takes place, less nitrous oxide is lost, and less nitrate is lost by leaching. So this is a process to control how the transformation of your urea all through the chain of the process of urea to nitrate. So this slide shows the production of nanoscale phosphorus from conventional source. So in this case, you use rock phosphate, which is a physical means. It can be two-way actually. It can be physical or chemical. In the physical means, you just simply take your rock phosphate, you crush it into powder. In this case, this is not nano powder. You can iterate this process several times to reduce the size from this bulk material here, bulk powder here, to nano powder. And then you have your so-called nanophosphorus through a ball milling process. If you take one of the iterations here and you add it to acid, like sulfuric acid, you dissolve this product completely into solution, and you add your alkali, you precipitate, and you have your chalky material here, which is the suspension of the phosphorus as nanomaterials. You dry it, you have your powder. So these are ways you can produce your nano-scale phosphorus. You can also do it chemically, like wet chemistry. In this case, this is the same process as the one I showed before, but with no urea added. You have your phosphoric acid, you add calcium hydroxide, you add your alkali, you get precipitate like these ones. You do all your characterization, you adjust the pH, and you can get different sizes based on adjusting the pH. I will show you some graphs later. You characterize microscopy, particle size, spectroscopy. You have your product, and this it looks like this in the image. The same process for zinc. You take your zinc ore mined from somewhere. You ball mill several times. You get your product. Several iterations will give you nanoscale zinc. You clean it. You have your product. Or you can do the bottom-up approach, where you take your zinc salt, in this case zinc sulfate, which is a conventional type of zinc that farmers use also in some places. You dissolve in water. You add your alkali, and between pH 9 and 12, you have precipitation. You characterize microscopy, surface charge, the hydrodynamic size, you dry, and then you obtain your powder. So these are this process here is what you see here. And if you adjust the pH between 9 and 12, you can get different types of particles. You can get roundish particles, you can get cuboidal particles, you can get rod-like particles. So just by playing with the pH, you can get different types of nanoscale zinc. So let's look a little bit at the fate of nanomaterials in the environment and the implications for fertilizer efficiency. So this image shows the generalized fate of metallic nanoparticles in the environment. So there are three fates basically: aggregation, dissolution, and surface coating or stabilization. Here you see the individual nanoparticles. Under certain conditions in the environment, they will aggregate and form clumps. This process is completely reversible if the condition changes to what makes that can reverse it. As one of them being pH, being salinity, and being certain organic acids in the soil can cause this process to move towards this way or go towards that way if it reverses. And when you have aggregation, what you see is that you have several outcomes. You have modified mobility of the particles. You have reduced reactivity, regulated metal accumulation, and all sorts of effect on the plant. The other fate can be dissolution of the particles. So here you have like silver nanoparticle, zinc oxide nanoparticles dissolved into silver ion, zinc dissolves into zinc ion or zinc hydroxide ion. The same goes for copper and for zinc and for iron. And when all of these dissolve into ions, the ions don't exist in the soil per se. They form complexes with anions like organic acids or even phosphate. And you have new products like silver sulfide, zinc phosphate, copper sulfide, iron phosphate, copper cysteine, zinc sulfide. All of these all of these compounds have different reactivities compared to original compounds, compared to the dissolved ion, and compared to the original particles. Therefore, you have modified effect just like you have in the case of aggregation. And these effects can be can be enhanced, they can be diminished, depending on the chemistry or in the soil and how they interact. And the last phase will be surface coating, which is essentially to stabilize the particles. So in the soil, these particles will come in contact with organic acids, such as citric acid or tartaric acid. And if these acids or organic matter, if they coat on the surface of the nanoparticles, the chemistry is modified. They become more stabilized in the soil because there's no interaction between them and the outside environment. That interaction is blocked by the coating material. Therefore, you have persistence and stabilized products that can be used as fertilizers. This is one of the things that when you produce fertilizer, nanofertilizer, this is one of the things you want to have. You want to have stabilized products that will respond differently from ionic or aggregated products. So we have seen that particle shape has a role to play in how they dissolve. Example here, there are three types of copper oxide particles here: the spherical ones, the rods, and the spindles. You can see, and these fellows here did some studies, dissolution studies, and they found that the spheres, these ones, the round ones, dissolve almost immediately, and then plateaus out, and then the rods, these ones dissolve less rapidly compared to the spindles. So if you want to develop fertilizers containing copper oxide, you may think of the shape of your product as spheres, as rods, or as spindles. This is important because if your soil is deficient of copper, for instance, and you want to supply the plant with copper immediately, you will be thinking of something that dissolves very quickly. So that will be the spheres. But if your soil has copper, you just want to maintain the soil copper levels. You don't want to go to the spheres that will dissolve immediately. You want to use rods or spindles that will be slowly but steadily dissolving to supply the plants what they need and have a reserve in the soil left over. So how can we stabilize nanoparticles in a very simple way? This fellow here, they show that what you want to do is to prevent these particles from aggregating. You don't want them to come as clumps because that reduces their efficiency. So this is iron nanoparticles produced, is clumped up, aggregated. So just by adding starch, this fellow added starch to it. The starch served as a dispersant to separate the particles, and by so doing it increases the electrical double layer, which is something that keeps the particle apart. If the EDL is low, particles will come together and aggregate. So, but just by adding starch, you cause a dispersing effect, and that reduces the aggregation. You can see compare these bulk particles here to the individual nanoparticles here. So this product is more effective, will be more effective as a fertilizer compared to this product because they're small. The plants can take them up directly, or they can dissolve in a very in a more efficient way compared to this product here. So this is just a cartoon of types of nanofertilizers that can be produced. You can just decide to produce just your simple true nanofertilizers. This can be like nanophosphorus. It can be zinc oxide nano. It can be ammonium nitrate nanoparticles, and use them directly as nanoparticles. However, it may be another way may be to form to produce nano-enabled bulk fertilizers. So you take your nanomaterials and you formulate them on top of a bulk material. So this is the bulk material here. It could be anything. You just add your nanomaterial to it, and you have a nano-enabled fertilizer. Again, you can do that on the surface. You can do that in the core, in the center of the bulk material, or you can just disperse the nanomaterials within the bulk material to form a nano-enabled product. This is just another cartoon to show the same thing, and these are the texts for that. So let's look at some effect of nanofertilizers in the agricultural systems. So this was the nanomaterial, the nano urea I showed you the last time, where you have the improved controlled release of the nitrogen from the nano urea compared to the plain urea. So when this fellow tested this in the crop, this is rice. You see the effect on rice yield. So this is no fertilizer, and this is urea. This is this urea here at 100 kilograms per nitrogen per hectare, and this is the nano urea here at 50. So half the rate of this one was used here, and you see an effect. This effect may not be very significant compared to this, but when you consider that you use half the rate compared to this, several things are happening here. You are saving your money, you are saving your product to use for the next season, and you are having a marginal effect on the yield compared to this. So clearly, by using nano urea versus urea, you can use less input of nitrogen and yet have similar or if not better yield compared to the bulk to the conventional urea that farmers use. Same effect was found with nanophosphorus. So here this was the other nanomaterial nanophosphorus I showed in the last slide. They use this material and treated on soybean that are 15 weeks old, and this is what you find here. So this treatment here is nitrogen plus the nanophosphorus at 22 milligrams per liter. So, and this is nitrogen plus the normal phosphorus, which is a single superphosphate. This is nitrogen alone, and this is control alone. So if you walk back this way, you can see just by adding nitrogen, you have a better effect than the control. By adding the phosphorus, normal phosphorus, you have a better effect than the nitrogen alone. By adding nanophosphorus, you have a better effect compared to the plain phosphorus. And this is the material that gives the effect you see here. So again, like nitrogen, you see clear role of nanoscale phosphorus on plant development. So this graph compares several micronutrients like copper and zinc on microbial growth. So this is for bacteria and this is for fungus. This bacteria is a so-called plant growth promoting bacteria, which supplies plants with things like hormones and metal chelators. And when you test copper oxide nanoparticles on this bacteria, progressively from 20 to 500 ppm, at 500 ppm, the bacterial growth is completely diminished. There's no cell is surviving. All the cells are dead. If you compare the nanomaterial at 500 ppm to the bulk copper oxide at the same rate of 500 ppm, there's no effect of this material because it's a bulk material. Solubility is low, it's all aggregated, and no ions are coming out to affect the type of effect you see with the nanomaterial. If you look at the fungus, this is a pathogen, and you want to inhibit pathogen growth so your plants can do better. So you add your zinc oxide nanomaterials at 500 ppm. You see a significant drop in the growth of the fungus compared to the control after 7 days. If you add your bulk zinc oxide, so not nanomaterial, you have a drop, but not as steep as the drop for the nanomaterials. And if you add your zinc ions at this amount, 89 ppm, this amount is the amount of zinc ion that dissolved out of this zinc oxide nanomaterials. You see that again, there's an effect, but not as much as the nanomaterial. So here you can simply say that there's a nano specific effect because size does matter. Even though this material releases zinc salt like you see here, the effect of size is also there to further increase the efficiency of the zinc oxide. And if you look at the effect on plants, here they use a lower dose, 10 ppm. The control, the bulk zinc and the nano zinc. So clearly there's effect of nano zinc on the growth of this plant compared to the bulk zinc, and of course compared to the control. Again, back to the fungus, Fusarium. This work shows that if you increase the dose of the nanomaterial zinc oxide from 100 to 500, you almost decimate the growth of the fungus in terms of the hyphal radius. Now you take this material here at 500 ppm, you test it in plants. This plant that is infected with fungus. This plant is a control plant. It has no fungus. You can see the stem is green and the roots are not rotted. This plant has fungus in it, you can see the stem is, if you look in this green arrow here, you see the fungus, the hyphae and the mycelium, they are growing here, and it's affecting the plant. The roots are rotting in both cases. If you take this product here and you apply to this plant here, well, this is what you see. The fungus here is diminished, and the rot is also abated a little bit compared to this. So there's an effect of what I would call a pesticidal effect of the zinc oxide, which reduces, which with increasing growth reduces the fungal growth on the plant. And this happens after 14 days. It's likely that as time progresses, this effect will become even clearer, that this product can diminish completely this if disease effect, so you can have your plants as clean as these ones here. So this shows the release of zinc from zinc sulfate, and nano zinc oxide, and bulk zinc oxide. You can see that within 70 hours, all of the zinc, actually in less than 10 hours, all of the zinc, almost all of the zinc you added from zinc sulfate, which is the salt, dissolve very early. So you see almost 100%. This will be like 95% dissolve, and you have so early, and you have a plateau. If you look at the nano zinc, the dissolution rate is lower and it's continuous. And if you look at the bulk zinc, it's very low and it plateaus out. So this we know that in the soil, zinc efficiency in soil is actually lower than the regular fertilizer like nitrogen or phosphorus. It's about 10%. So by understanding how zinc releases in the soil, we can design our products. In this case, the preference would be to design your zinc as nanomaterial, because you don't want too early release, because this zinc that is released here as zinc ion is tied up as phosphate, as citrate, as whatever, and they are not easily soluble available to the plant. You want a slow release that goes on throughout the life cycle of the plant, and you don't want something that is not released at all, like in the case of the bulk. So nano zinc represents a strategy to increase zinc use efficiency in plant systems. So I'm going to be going more into zinc because you found out the reason why zinc is very crucial when it comes to places like Africa. If you look at this map here, this is a map showing the zinc status of the world. So you can see most part of sub-Saharan Africa, and some part of Asia, and some part of South America, and a few places in the US and also in Australia. They suffer from zinc deficiency in the soil. However, zinc is very important, is one of the very important nutrients in plant and in humans. It's involved in numerous, over 300 enzymatic activities in biology. And the activities we see in plants, for example, drive what we see as yield or as growth, so agronomic outcomes. 50% of the world's, like I said, you can see 50% of the world's soils are zinc deficient, and a third of the world's human population suffer from zinc deficiency. Zinc deficiency is very rife in places like Africa and also in other places in the world. You can see this kid here suffers from zinc deficiency. So the role of agriculture will be to see how we can use fertilizers, feed them to the crop, and then use the crop to feed the humans, so that this type of zinc effect will be less obvious. To make matters worse, the US Geological Service has a data that show that the world's zinc reserves is depleting very fast, and it looks like in the next 25 years we'll be running out of zinc in the soil, barring the discovery of new mines in places that are not known yet. So in view of the above, all of these issues, there's need to use less zinc in crop production. Hopefully we can do so without any agronomic penalties. I have found in my studies that using zinc at very low rates of 6 ppm and below has several benefits, which includes the acceleration of plant phenological development, like example, under drought, the promotion of grain yield, which can happen both under drought and non-drought condition, the enhancement of nitrogen use efficiency, which I have seen to be quite plant specific, and it is in support of edible tissue fortification of zinc for human and health and nutrition, which is what I was trying to explain here. You feed the plant with zinc, and then the humans can feed from the plant and get the zinc into the system. So we'll run through some examples here. This is example to show the acceleration of reproductive development under drought and the role of zinc in this system here. So these plants were grown under drought, 40% feed moisture capacity. So you subject the soil and the plant to drought at 40%. And then you add your zinc oxide nanoparticles at 3 milligrams per kg, so 3 ppm. So two things are very obvious here. The effect on flag leaf. Flag leaf is the last leaf that comes out of the plant before the grain is formed. And then the other parameter here was grain head. So this is what happens under normal moisture conditions, so no drought. If you add your zinc at 3 ppm, your flag leaf is formed after 43 days, and your grain head is formed after 46 days. Now if you introduce drought at 40% moisture, and you have no zinc in this system here, the flag leaf is formed after 59 days. So you look at the difference between this day and this day. So there's a delay of development due to drought. And if you look at the grain head, it comes out after 63 days compared to 46 days. So this is the effect of drought here. Now, under the drought system, if you add your zinc at this rate, you bring down the number of days to development from 59 days to 47 days, and you do same for the grain head from 63 days to 51 days. So clearly, drought delays development of plants, and by adding zinc, you can facilitate development. The mechanism is thought to be the role of zinc in regulating hormones such as abscisic acid and auxins. These hormones are involved in plant-water relations and in phenology. So by adding the zinc, you provide the active material to facilitate enzyme activity, and then the hormones can become active. So these are these plants here, just to prove that this is not just data, it's in real life. So this is the drought with no zinc. This is drought with zinc, and this is no drought with zinc. So on this day X, you see the grain head is formed, fully formed here. On the same day, the grain head is emerging where you have drought and with zinc, and on the same day, you don't have any grain head emerging. So clearly zinc does something here compared to this one, and water is active in this case compared to this one. And the zinc is just particles like that. So effect, again, effect of nanofertilizers on grain yield here. In this case, soybean. So what we did here was we did what we call nutrient omission studies, where you have all the nutrients. In this case, we have all the nano and all the bulk. So all means you have zinc, you have copper, you have boron as nanoparticles. So you add them in the soil, you grow your soybean, you see the effect compared to the control. You do same for bulk, so all these nutrients, and you grow your crop, you see the effect as a bulk fertilizer. There's no difference between the nano and bulk in this case. However, when you omit, now you want to see which of these nutrients is causing the effect you see here. When you start omitting zinc, copper, and boron stepwise, when you remove the zinc oxide, the zinc from this all, you see the effect goes back to the control. That tells you immediately that the zinc in this place is active and is involved in this effect you see here. When you remove the copper, there's no effect. You remove the boron, there's no effect. And the same also for the bulk. However, for the bulk zinc, when you remove the bulk zinc, you see a reduction in the yield compared to the bulk all. That tells you that the zinc is also active here. But when you compare this to this, the zinc is more active as a nano than as bulk. So there is a nano-specific effect, which you see comparing this to this, and there is element-specific effect, which you see when you compare zinc, copper, and boron. No effect, no effect, effect, and effect. I will talk about the implication of this in a later slide. Again, the same study, we are looking at how you can use nanomaterials, in this case, again, zinc oxide, copper oxide, and boron oxide nanoparticles to increase nitrogen uptake in plants. So this is the mechanism here. Zinc and copper are urease and nitrification inhibitors. Remember what we talked about the last time about inhibitors. They reduce the rate of nitrogen loss. by regulating transformation of urea to ammonium and ammonium to nitrate. And with that effect, you have minimized loss of ammonia and you have increased nitrogen accumulation. So what you see here is that when you have the all nano here, you have more nitrogen taken up in the plant compared to the control. When you have the all bulk, there's no effect compared to the control. And when you start taking out the elements, the nanomaterials one after the other, when you take out the zinc oxide, you have reduced nitrogen uptake compared to the all bulk. And for the copper also, you have reduced nitrogen uptake compared to the all bulk. You don't see the effect with boron, and you don't see the effect with all the bulk materials compared to the all bulk. So this shows clearly again a nano-specific effect. So nano here and nano here, and zinc and copper effect, which is what you see with zinc here and with copper here, but not with boron in the case of nanomaterials. So how can we fortify our crops with zinc to meet our human zinc needs? In this case here, this is sorghum plant grown under drought at 40% feed moisture capacity. And here you have the amount of zinc taken up. So this is the non-drought condition. You have higher zinc uptake in the grain. And with drought, the control, no zinc added, you have reduced zinc in the grain. And when you add your nano zinc at 1, 3, and 5 ppm, you have increased zinc, not quite as much as the non-drought condition, which has 3 ppm zinc, because drought is known to reduce nutrient mobility and therefore nutrient uptake. If you extrapolate these numbers here and convert them to actual concentration, so like ppm, these values are amount per plant, so milligram per plant. You convert them to actual concentrations to see how much of the zinc is in your grains. So this we convert to, for the case of zinc added at 3 ppm, where you have water availability, you have 45 ppm of zinc in your grain. And when you have no water and you have no zinc, you have only 19 ppm. When you have no water, you have zinc at 1, 3, and 5 ppm. You have 37, around between 37 and 30, between 36 and 38 ppm of zinc in the grain. So comparing this scenario here, where you have water and 3 ppm zinc with no water and 3 ppm zinc, you have 15% reduction caused by drought. So keep that in mind, that drought can reduce the quality of your plants in terms of the nutrient content. So, and with that in mind, if you add your zinc under drought, what can happen? What can happen is this. In the case of the plants without drought, so no drought and with zinc, you can obtain up to 59% of your recommended dietary allowance for zinc, because you added the zinc and there's water to take the zinc up and feed the plant, and the zinc will go to the grain. If you have no water, you can only get 25% of your RDA. If you add zinc between 1 and 5 ppm, you can get between 48 and 50% of your RDA. Now compare these values here to this value here. You will see the effect of adding the nanomaterials under drought conditions. And if you compare these values here, especially this value here to this value here, because you are looking at the same scenarios in terms of amount, you're only losing like 9% of the zinc due to drought. So you are bringing from 15% to 9%. So this informs us that if we feed our crops with nanomaterials at very low rate, these rates are, if you go back to the previous graph, you see here, these rates are 2 ppm, 0.5 ppm, and 1 ppm of this material. So that's very low rate, not toxic. You can feed your plant with zinc, and then hopefully such effect as we see in this kit here can be negated. So let's talk a little bit about green chemistry. I know that most of you will be interested in so-called bio-nanofertilizer. So let's compare a little bit nanofertilizer versus bio-nanofertilizer in terms of what it takes to produce them. So the goals of bio-nanofertilizers, bio-nanofertilizers are fertilizers developed by using plant extracts, as I explained that previously, to convert conventional nutrients to nanonutrients, or to nano-enabled conventional nutrients. And what are their goals? On top of the goals of nanofertilizers, as described previously, there are additional goals for bio-nanofertilizers, and those goals include to make nanoscale materials more biocompatible via surface modification. So you want to reduce or eliminate toxicity as a result of the nanoscale property of your fertilizer. And then by so doing, you are reducing the environmental footprint of nanomaterials or of the technology itself in agriculture. So biofertilizers versus nanofertilizers. If you look at this box here, the red box, there are several processes that must take place. I chose to call those processes preambles. So to have bio-nanofertilizers, you have to have the microbes or the plants, and you have to screen them for the extracts. What extract do they produce? How efficient are the extracts? What amount can you produce? How can you scale them up from flask or from greenhouse to bioreactors, and then take them to the greenhouse and then to the field? And how do you grow and process the bio? And processing will mean you have to filter them, you have to centrifuge, you have to characterize them for the extract in terms of protein content, organic acid content, enzyme activity, and all sorts of activities. So this is a rate limiting step. This is a step you must take before you can start, and these are all the so-called bio steps you can take before you can come to the nano itself. And the nano will mean taking the extract from all of this process here and mixing it with your regular nutrients to form the bio-nanofertilizer, which will be surface modified. The enzymes and the organic acids in this system here, we act on the nanofertilizer, modify their surface to to make them more biocompatible. Then you process them by centrifugation for filtration. You wash, you dry, you characterize. You have your nanomaterials, and you apply them as bio-nanofertilizer or bio-enabled, nano-enabled bulk fertilizer. Now, compare this process to the regular nanofertilizer that does not have all of these steps here. You just go straight to this step here. This is the step. This step here is what you have here. You just process your nanomaterials, characterize them. You have your product, either using the top-down approach or the bottom-up approach. It's a faster step, and this is a slower step, but because you have this process here to take care of. So it is something to keep in mind when we promote bio-nanofertilizers versus nanofertilizers. This is very good in terms of eliminating or reducing toxicity, but you have to deal with all of these steps here first before you get to the process that you can start comparing with the conventional nanofertilizers. Let's look at some perspectives on what we need to do to scale up and commercialize bio-nanofertilizers or nanofertilizers, as the case may be. So this is a generalized conceptual framework, and as with everything R&D, first steps are involved. You have to conceive your innovation, you have to train your human resources, you have to set up your material resources, and then you have to produce and then find end users for your product. So in this case, we are dealing with nanofertilizers, which if it is bio-nanofertilizer, then you have to consider again the bio steps, the plant, the fungi, the bacteria, and the other products like chitosan. You have to extract all of these, process them, characterize them, and then apply them to the nanotechnology, and then apply that nanotechnology to the fertilizer, produce your fertilizers, and then decide at this stage what types of product do you want: foliar, seed dressing, or soil. That will be for the end use. So to get to this point, if you are doing nano, you have to again deal with this issue. If you are doing bio nano, you have to deal with this issue first. If you are just doing nano, then you start from here, produce your nanomaterials, convert them to fertilizer, and then you have products you can claim as R&D. So let's talk a little bit about scaling. Scaling simply means expanding or increasing the size, reach, and variety of your material. In this case, of bio-nanofertilizers. So there are three types of scaling you can think about here. You can think about scaling up, which is the increasing the volume or amount of a specific nanofertilizer, example, phosphorus. So this cartoon here shows that we can have a nanophosphorus material in the lab in gram amounts, we can run experiments with them and get good results. But that's not what the farmers need. You need to move this to kilograms and test them in the field to see how they play out in the field, in the real environment where a lot of complicating factors are involved. Then when you see good results here, you mass produce this nanomaterial, now nanofertilizer, in tons, and it goes to the market. So you're increasing the volume from lab scale to greenhouse or field scale, and then to the market for one product. Now you want to scale deep. The second type of scaling is scaling deep, where you change the culture. As we know, old habits die hard, and people are used to applying certain types of fertilizer in their farm, which is the normal fertilizer, example like you see here. Now you have to convince a farmer that, hey, this fertilizer is not as good as a nano fertilizer. And how do you do that for something that they don't see with their naked eyes? They have to use a microscope to look at them to see the individual particles. So that will be a task to do, to convince someone to move from using regular fertilizers to using conventional fertilizers. And not just for the farmer, you also have to convince the industry that will produce the nano fertilizer that this is better compared to what they're already doing. Again, for a single product. Now to scale out, as we know, crops need about 14 nutrients. So which of the nutrients do you scale out or do you scale up? Possibly not only one, you have to scale up several types of nutrients as your soil test shows you what is lacking in the soil. So you have to develop, example, in this case, tons amounts of nitrogen at the same time as you're doing of phosphorus, of potassium, of zinc, of all sorts of different nutrients. So three things are involved. Yes, three types of scaling. You scale up, you scale deep, and you scale out. Some factors to consider when you are scaling up your bio-nanotechnology or that is to be applied for the fertilizer industry. So the question will be, what types of nutrients do you want to scale? Going to the literature shows that most of the studies that we have done have been with micronutrients. So things like zinc, copper, boron, manganese, iron. Those are good, those are essential nutrients, but they are not the most important nutrients that plants need. Plants need NPK more than these other nutrients. And industries are more focused on producing NPKs. But the literature shows more studies with micronutrients than with NPKs. At least the original literature. But now things are changing. There are more and more studies coming up that shows how you can apply nanotechnology to nitrogen, phosphorus, and potassium, and how those nutrients compared to the conventional nutrients that farmers and industry are used to. Then you have to think about the type of formulation for your nanofertilizer. You want to coat on the surface, you want to cap, you want to embed in the material, or you want to coat, you want to put in the core of the material. And this question will be answered for each of the nutrients, looking at the chemistry of the nutrient and how the materials you are adding interact with them. Then the question will be asked, what is the source of your raw material for formulation? Are you going to be using microbes, bacteria or fungus? Are you going to be using plants, or you're going to be using naturally occurring minerals? There are certain minerals like zeolite, like atapogite, the one I showed before, that can be used to produce nanoscale fertilizers. So which of them is feasible in terms of economics of production and processing? And how easy is it to use this or produce the raw materials and the extract that will be used? How rate limiting will that be for your process? And then, of course, how feasible is the process for incorporating raw materials with nutrient elements at the nanoscale? It's not so easy for some of them. It's easier for others. I think elemental metallic nutrients are especially more easy to deal with than phosphorus. So scaling deep, changing the culture, very important, because you have to convince a lot of people that what you have is better. So you have to show that nanofertilizer is superior based on scientific and demonstrational evidence. So which nutrients are you talking about? NPK, secondary or micronutrients are better than the normal nutrients at the nanoscale. You have to deal with the soil chemistry. This soil chemistry is one of the most crucial things to think about when you are designing nanofertilizers, because things like pH, nutrient status, organic matter content, they all affect how your nanofertilizer respond in the environment. I'll give you this example here. This soil here contains zinc at 0.1 ppm. So this zinc content is very low. The same soil contains boron at 0.5 ppm. which is normal for boron in most soils. The same soil contains copper at 0.4 ppm, which is about normal for most soils. Now, you grow your plant in this soil. You put your zinc, boron, and copper nanoparticles. Again, I showed you this before. This is what you get. You get a response with zinc, both as nano and as bulk. And the reason is because the zinc here is very low. Assuming this zinc is not low, and you add the zinc, you get results like this where you have no effect of your fertilizer in the system. So while designing your product, you have to go back to the soil chemistry again to look at what goes on in the soil, and then that informs the type of formulations you design and produce to be able to see effect like we see here. We knew in this case that the soil had low zinc, so we added zinc at 2 ppm to make sure that it covers this deficiency here, and then you see clearly the effect. The response was higher compared to copper and zinc. So if you consider the environment that you want to apply your material in. Normal environment, biotic environment. Example, I showed you the effect with bacteria and fungus. So this could give you what we call multi-functionality. Your fertilizer is not just for growing crop alone. It can also be for killing the disease, or it can be for improving plant growth under drought stress, like I showed you. So consider what kind of function do you want to give to your product that is just beyond the normal effect you see as yield increase. Then you have to decide what application rates. Biomaterials are very reactive, as like I mentioned. So just by playing around with rates, you can see effects that are extreme, from toxic to non-toxic. So you have to decide by experimental means what rates are suitable compared to the conventional fertilizer. Again, you want to make sure that you are using lower rates that will give you the same effect as the normal rates. So you want to eliminate any yield penalty. Then you decide what application routes are you going to take. Soil product, foliar product, seed dressing. Even I see now some people are talking about stem injection, how to inject like things like banana. They have a very watery stem. Inject them with nano-scale nutrients and see how the nutrients are mobilized into the plant. So that will be to show the evidence that this work and they are better than the conventional materials. But that has nothing to do with the industry itself. Now you have to consider the industry. What do they need? How do you need to convince them that your nanofertilizer is not disruptive to their industry? Because industries have already set out standard operating procedures. Difficult to change those procedures because they're expensive and they are already set, almost like set in stone. So the questions will be asked: will it require overhauling our system, or will it require making huge investments in our new plant, in new plants? If so, at what cost? And is that cost profitable? And do we make profits from changing our system to accommodate your nanoscale fertilizers? At the end of the day, you have to now show the effect on the profit itself. So the question will be: do they improve crop yield so much that when you compare to conventional fertilizers, you have a service in terms of more crop yield and less nutrient use? And which goes to the question also of whether that will lower your cost of applying fertilizer in the field compared to the conventional product. At any rate, a good nanofertilizer practice must be soil specific. It comes back to this: you must test your soil to be sure you're not adding what the soil doesn't need. Otherwise, you waste your money and you don't get the effect like you see here. Now, scaling out, producing different types of nanofertilizers. So in many parts of the world, the soils lack multi-nutrients at the same time. So you can do a soil analysis and you find that copper, zinc, boron, nitrogen, phosphorus are all lacking in the soil. So what do? You are tempted to produce one single fertilizer that contains all of these nutrients. That may work for that soil, but in other soils, maybe only boron and zinc are lacking. The other nutrients are not lacking. So that will inform what do we need to scale out. Do we need to consider the multifunctionality of fertilizers? So like I said before, not just to improve yield, but to improve nutrient use efficiency, and to improve the produce quality and the resiliency to stress like drought and disease. So for that purpose, do we need different fertilizers, or do we do one size fits all nanofertilizers? What types of formulations, singles or different nutrients, composites of different nutrients, and what are the ratios of each of those nutrients? A lot of background studies have to be done in terms of plant nutrition, soil fertility, and the chemistry of all of these nutrients and how they interact with each other. So it's not advisable, in my opinion, to do a one size fits all, because each soil is different and each plant is different. So to produce a so-called mega nano fertilizer that will contain all sorts of ions, like iron sulfide, phosphorus, copper, zinc, and then add them to a soil, it may not make a lot of sense because of its differences in soil. In the real world, and again, fertilization will always be crop and soil specific, and that is based on soil testing. So the question will be, how desirable is bio-nanotechnology for a place like Africa? It looks like it's going to be desirable because already in Africa we use low amounts of fertilizers. So anything that supports that that low use of fertilizers will be welcome, and nanotechnology is one of them. And bio-nanotechnology improves that even further by making the materials less toxic. However, a lot of things need to be considered also that is specific to developing countries. We don't have they don't have in those countries the human and the adequate human and material resources which will be involved in processes for the industry. For example, the industry will need to set up new bio facilities, or they will use that is separate from what they are doing, or they have to so would they set up their own industries, or would they have like contracts with people who will produce the bio preambles for them, and that will mean to maintain the plant and microbial cultures, which is not trivial, and to prepare all the extracts needed for the nanofertilizer. These questions will be answered if we have enough human and material resources to deal with that. Then we think of how to ensure the standards are optimized in terms of extract quality, so that we have consistency and reproducibility. So, like for example, if you use a certain plant to produce your extracts, and they use another plant to produce the extract, likely not the same extract in terms of quality, in terms of the enzymes, in terms of the organic acids contained in them. So do we have to optimize all of that using one single plant, or do we have to study, experiment with different plants and then come up with the best plants that gives us the best outcome in terms of extract quality and quantity? Then we think about the economic feasibility of the extract itself, comparing the microbial, the plant, and the natural organic acids like organic minerals like sodium humate, attapogite, and zeolite, some of which can be found in Africa. So it might be just easier to deal with them than having to plant crops or grow microbes in bioreactors and produce extracts that can be used. So very importantly, we have to deal with the perception, the public perception of nano as being toxic. It is true that nano is toxic, but it's not a wholly true story, because the dose is very important. At lower dose, you see virtually no toxicity, like I showed in some of the images before. So it's the dose that makes the poison, not necessarily the nano itself. So we have to change that perception that nano is toxic, just using science-based evidence, especially field studies. You have to test your products in the field, just beyond the greenhouse, and see how they play out in the complex environment. With that, you can prove benefits of nanofertilizers. We are using rates that are relevant to agriculture, so no overdosing. And we have to, importantly, we have to develop efficient and safe methods to apply the products at field scale. And for example, here, this is conventional urea. You can just take this conventional urea and you broadcast it in the field. This is what most farmers do in Africa, just broadcast in the field. Because this material is heavy enough, it will sink into the ground, and then the plants can use them. However, this is not the case with nano. Nano is very light. If you take this nano powder here and spray it like this man is spraying, it will drift. It will go into the environment because it's lightweight and cause harm to even to the farmer himself, or to some other organisms that are present in the environment. and very little of that will get back into the soil because it's lightweight. This is worse if there's wind. So there will be particle drift and suspension. So you cannot be doing surface broadcasting with nanomaterials. So you must find an efficient and safe method to apply nanomaterials in the soil. So one way to do that would be to make sure that it's not disruptive to the industry. So the industry will ask the question, are your nanofertilizers inherently disruptive to my process? If they are disruptive, they will be disruptive if the industry has to modify their process to accommodate your technology, because it's too removed from what they are doing, from their standard operating procedures. In this case here, this will be something that will be disruptive. So this is a cartoon showing what the industry does. So they extract their minerals, in the case of nitrogen from the atmosphere, phosphorus from the soil, and potassium from the soil. They prepare them, separate, concentrate, granulate, blend, salt, and they have their finished fertilizer in a bag, like this bag here. So if you introduce your nanotechnology within this process, within this block here, it will disrupt their process, because this is what they do, or this is what they know how best to do. And you are bringing a new process that they have no clue about. They may likely not buy this process because it's going to be disruptive to them. However, if you take this process and apply it at the end of process, at the end of their process, so they have their finished product, and you incorporate your nanotechnology at this point, which you can do by spraying the finished product with your nanomaterials. It can be zinc, it can be chitosan, it can be anything that will confer nanoscale to this product here. This can be bought because this process here has nothing to do with their line process, as you see here. This is after they have the product already made. You apply your nanotechnology, and then you have new products. I will show you some examples in the next slides. So these are different types of nano-enabled urea products. So this is your normal urea. As you know, urea is white in color. If you apply nanotechnology, like in this process here, where the product is already made, so these are presumably urea granules. You can just take your nano powder, like in this case zinc oxide, and you formulate the zinc oxide onto your urea, so on the surface. In this case, because the product is already made, you can do that in a very simple method involving vegetable oil, food color, and you only need a mixer or fluidized bed. So you mix all of these components, and then you have different, depending on the food color, depending on the color of the food color, you can have yellow, green, blue, or orange color products. You can do same also with copper and with boron. In this case, copper is dark in color. As you may know, copper oxide is dark in color, so you don't need the food color when you are dealing with copper oxide coating of urea, because it's already dark. Once you coat the powder onto urea, it becomes dark like this. For zinc, you need a color, you need food color, because you need a color material, because urea is white and zinc is white. So to let you know that your system is working, you have to add a color to it so you can see and you can visualize the effect. And when you do that, this is the type of results you can get. So this is urea coated with vegetable oil and food color, and there is no zinc, no nanomaterial. This is the plant, and this is the yield here. If you coat urea with vegetable oil, food color, and with nano zinc oxide, this is the plant, this is the yield, and you are coating with 1%. This represents zinc that is not coated, but the zinc is present as nano. So there's nano here, there's nano here. There is no effect of coating compared to non-coating. If you look at the bulk, with the bulk zinc, again, this is the plant and the results. Coating with 2%, coating with 1%. Coating with 2% of the bulk and coating with 1% of the nano. If you look at the nano scale material here, the effect is similar to the bulk material, but you have 1% zinc and you have 2% zinc. You have 50% saving of your zinc. Now, if you compare the coating itself, coated and non-coated, no difference. So you wonder, why do I have to waste time producing all of these things? If you go back to this slide here, you see that you cannot do this because the nano is so small. You cannot apply the nano by itself in the field. The only way you can do that is by coating, which is what we did here. So this is greenhouse, so it's easy. You can just add it directly in the greenhouse, but you can't take this to the field, this particular one here, because it's not coated. You can take this to the field because that's what it represents here. So you don't have any advantage of coating in terms of yield, but it can facilitate your application method in the field because you can take this product directly to the field as urea and apply them, but you have the nitrogen as nano on the urea itself. So I'm currently working on studies looking at formulating phosphorus from TPP. TPP is tripolyphosphate with nanochitosan and zinc oxide nanoparticles. So as you know, phosphorus is the second most important nutrient in the world that plants need. However, efficiency of phosphorus is low. I think it's less than 20% or so. And we have a source of phosphorus called tripolyphosphate that is produced industrially and not used as fertilizer. It contributes it leaches into the environment and causes eutrophication. If you look at detergents that people use to wash their laundry, it contains phosphorus, and that phosphorus is TPP. So how can we harness TPP as a fertilizer source? And to do that, how can we minimize certain interactions? If we add zinc, for instance, we know that zinc and phosphorus don't interact positively that much because they form insoluble zinc phosphate that disallows the uptake of both phosphorus and zinc by the plant. Example here, you look at this graph here. So this is control plant with only phosphorus. This is the much phosphorus taken into the plant. If you add zinc to the phosphorus, you have reduced phosphorus uptake because it's interacting with the zinc to form insoluble zinc phosphate, which the plant don't take up easily. In the same system here, if you have this plant here, is this plant here, so you have less because more is taken up here. You have less in the soil. When you add the zinc, this is taken up, but you have more in the soil after plant harvest. So you can get double advantage. You can you can get one advantage and one disadvantage. This is the disadvantage here in terms of uptake, it's reduced, but this is the advantage here in terms of residual zinc in this phosphorus in the soil. It's more. This means you may have more phosphorus for the next season to plant if you have zinc in the soil, if the chemistry allows for dissolution to occur, and then you have the zinc released. However, to solve this problem here, I'm hypothesizing that chitosan can modulate this interaction here to prevent what we see here from happening. We want phosphorus to be taken up by the plant and not leach out into the soil, into the water. So what I'm doing now, I'm taking some chitosan and I'm adding that to TPP at low pH. This low pH will cause the chitosan to reconfigure and then cause a cross-linking between with TPP and the chitosan to form the nano-scale material. And then if you add the zinc to it, the zinc will just sit around in the complex with minimal interaction with the phosphorus, preventing this formation here. You see here, because you have the chitosan present that causes the cross-linking. I'm expecting that because there's a cross-linking of phosphorus and the chitosan here, there will be less interaction of the zinc. Therefore, there will be more zinc. There will be both more zinc and more phosphorus available to the plant in terms of uptake. But comparing to the normal phosphorus, this will be more efficient because there will be reduced leaching, there will be more uptake, and there will be better plant performance just by reducing the rate of leaching of phosphorus from the fertilizer into the soil. So in closing, we can go back to ask the question, can nanotechnology contribute solutions to the problems in African agriculture? I would say the answer is yes, and we can look at it in four aspects, as mineral fertilizers, as pesticides, as a solution to climate change mitigation. So I showed you some examples of using zinc to control the effect of drought and also of some pathogens, which we know are events occur more when there is under climate change conditions than not. On top of that, nanotechnology will support African countries that use low fertilizer On average, Africa uses about 15 kilograms of nitrogen per hectare, compared to places like China and the US, where they use over 100 kilograms per hectare. So by using nanotech, it may allow us to continue using low rates of fertilizer, but we use them more efficiently. That all of this will help us to feed our population while using less agrochemicals such as fertilizers. Thank you very much.
Thank you, Dr. Dimka, for such a holistic approach in using nanotechnology in terms of agriculture. And I think from the audience, you can agree with me to say that if at the beginning of this presentation, you were Thomas, and you didn't think that nanofertilizers have more advantages, has some advantages when you compare them with the fertilizers, Dr. Dimka managed to show you in this presentation that with nanofertilizers, we can be able to improve the plant growth of some of the plants that he worked on. And I would like, not to waste time, I would like to open the floor for the question and A. I will start first with the question and A from the chat. And I would also like the audience to raise their hand if they've got any questions before we can conclude. Okay, the questions from Q&A, I've got one from Blessed Okole. He would like, it's just a request. He would like to appreciate the presentation if it can be shared. So I think Samuel will assist us with that. And also if Dr. Dimka agrees with that. And then another question from Edson Mumba. He's asking, what about the cost in the manufacturing of the nano fertilizers? Will it not push the cost up? That is one. And then from Ayop Hajsat, he's asking, were good results obtained with foliar nanofertilizers? And did the fertilizers supported on nanomaterials, for example, nanosilica, give good UNE? So I think those are the two questions that we've got so far, Dr. Dimka.
Well, let's take the question of cost. Yes, okay. it will increase the cost, but I showed you several slides where if you use lower rates, you get higher yield, at least slightly higher yield. Lower rate means you are saving your money in terms of how much fertilizer you buy, or even if you buy like a full bag, you can use half of it. The next day you use the other half, so you don't. It saves you money, and in the long run, it may cost you more to buy it, but in the long run, it saves you more money, and you don't lose your yield. You get the same yield as those people who use the full amount of fertilizers. But as we develop this technology more and more, and as the industry catches up with it and start to mass produce products, the cost will definitely come down. So it will be a matter of scaling. Once you scale up things, the cost should be able to come down.
Okay.
In terms of foliar, yes, there is evidence that foliar application works, but from my own experience, I have not really seen any big effect of foliar versus soil, because most of the nutrients can travel both ways. If you apply them on the leaf, they can travel to the root. So we call it basipetal transportation. They can move from the phloem to the xylem and to the root. And if you apply to the soil, they can move from the xylem to the phloem and then to the other parts of the plant. So as long as the nutrient is mobile, I don't see any big deal in terms of how you apply it. The only issue with soil is that because of the chemistry in the soil, if you apply your nutrients, some of them will be maybe lost by leaching. Some of them may be complexed by things in the soil, organic acid, organic matter, all sorts of anions or cations in the soil will complex with your fertilizer and then diminish the effect. So that may be an advantage for using foliar. Other than that, in my hand, I've seen nearly the same effect for foliar as for soil.
Thanks a lot. And then we've got another question from, I think it's just a comment, Magwena Justice Muloto, thanking you for the presentation. And I think from your presentation, he would like to tap into the area using nanomaterials. So I think that's quite good. And he's also looking forward to possible collaborations. And then Manfred Scriber, his question is, does the nano zinc oxide offer value proportion to the industry? Price and performance, is the price and performance acceptable? And then a question from Makwena Justice Muloto. How much is nano used in the control of unwanted weed similar to the weed killers? And then also another comment from Manfred Scribbler, the presentation was excellent. So thanks a lot to Dr. Dimka for a great presentation. And then the last question from Ayop Hajset, another question from Ayop Hajset. He's asking if no, I think this is a repetition of the question that you've answered, yes. So I think so far we've got a question from Manfred Scriber and then also Makwena Justice Muloto. Over
Again,
to you, Chris.
one of the questions was on the cost of zinc oxide.
Yes.
The normal zinc oxide is not expensive. I mean, relatively speaking, is less expensive compared to the zinc sulfate. The normal zinc will be zinc oxide bulk. That's what most farmers use around the world. But it's highly inefficient because it's bulk material. It easily forms aggregate. It's not very soluble. I showed you the graph of it somewhere in my presentation. But if you use zinc sulfate, it's more expensive because it's produced synthesized in the lab, but it's highly soluble. Therefore, you end up wasting most of your nutrients. The plants don't take anything up, take little up from them. So at the end of the day, if you use nanomaterials, you may pay more initially, but at the end of the day, you get more because you use less, and then hopefully you produce more with it, or at least the same. You produce more or the same as the normal zinc oxide, but you are using less. So again, if you once industry begin to scale up, that should be a means of mass producing, and then the cost should naturally come down. Okay. That's what I think about that.
And then another one from Makwena Justice, how much is nano used in the control of unwanted weeds similar to weed killers? And I think I will take last more 3 to 4 questions. I think Dr. Dimka, if maybe you can answer that one.
Yeah, there's evidence that there are herbicides that are based on nanomaterials. Mostly what I would call nano-enabled herbicides. So you put some nanomaterials in the regular herbicides, and then that helps to enhance the delivery of the herbicides into the plant. So and they are very effective because you increase uptake of the herbicide from the leaf or from the root if it's systemic herbicide. So there's evidence. Whether they are in the marketplace as of today, I don't know a lot about that, but I do know from the literature I've read, there's evidence of nano-scale herbicides being used.
No, thanks a lot. I think let's take a question from Hulda Swai. I would allow her to ask her question. Please unmute, Hulda. Hulda, I think you can unmute yourself. You unmute yourself to ask your question or maybe to comment on the presentation. Thank you. Yes. Yes, we can hear you now.
What I'm saying is he planning to collaborate with industries or in some industries to upscale his technology or to convince them to use his technology?
You were cutting off. I didn't hear all of what you said.
Yeah, I know what you're doing is research or product development research, but I'm just wondering if you're collaborating with industry or you're planning to, so that you can upscale your technology or you can convince them to use your technology.
Okay, yeah, I get you. Well, we have some. We are talking to some companies now. Specifically, we are talking to OCP, and OCP in Morocco right now. So that will be one way the discussions will be one way to convince them with evidence, yeah, with the science behind the technology too, so that they can see about collaborating and then scaling up, because only the industry can scale this up. We cannot scale up. We don't have the means to scale up because we don't have the facility for that. So yes, we are working with some industries in terms of at least in initiating discussions with them.
Yeah, that's great.
Okay, no, thanks a lot. I think I would like to ask Prof. Maza to comment on Dr. Dimka's presentation, or maybe if he has any question for Prof. Dimka. Prof. Maza?
Yeah, it looks like we've lost him.
Oh.
We've lost him.
Yeah,
Okay,
yeah.
I think I will.
There's Kofi Adu. Maybe you can.
Yes, let's take Kofi Adu. Kofi, I think you can unmute yourself.
Yes, yeah.
Yes, thank you.
Chris, that was great. I really appreciate the talk. The question that I have is, one of the challenges that the farmers face, even with all these improvements using these nanotechnology, is the pest control. Now, are you looking into ways to make these plants also a bit resistive to pest through the approach that you are developing?
Yes, not me directly, but my colleague Justin White and with Elma, we all work together in the station here. They have been, and I think you met some of them in our last meeting.
Yes,
we have been using copper oxide, because we see that just like the copper pesticide, copper oxide is the most effective of all the elements in terms of service as a pesticide. So we have been using copper oxide nanoparticles at very low rates compared to other elements like zinc and boron and magnesium and manganese. We have seen very strong effects of reducing disease progression in the presence of plants. We've seen that in many plants, we saw that in eggplant, we saw in tomato. Mostly for now, we are dealing with vegetable crops, and the end game will be to look at those nanomaterials in real crops like arable crops, like the crops we have in Africa, cassava, wheat, corn, and that might be a place where collaborating with some folks back in Africa will be a very useful exercise to do.
Yes, and I think most of the West African countries where one of their biggest product is cocoa, everybody is aware of that, and there is so much chemicals that are used in taking control of these, and that could be one big area that if this research can have a great impact.
Yes, I believe so. Using nanomaterials for cocoa for suppressing disease in cocoa will be like using a foliar application of the materials will be a good way to go. Yeah. Because we've seen in our study that zinc and copper not only kills the fungus or the bacteria, it also confers internal resistance, so systemic resistance to the plant itself. So it's likely that one application can take care of several rounds of production before you apply the next time.
Yeah. Well, thank you very much.
Welcome. Thank you very much, Kofi. I'm taking the last two questions from Yamikani Kalolo. Is asking, for how long can nanofertilizer be stored before being used or applied? And then another one from Ayop Hatch said, are nanofertilizers safe for fauna? So those will be our last two questions, then we can close the webinar.
They can be stored as long as you store your regular fertilizers, as long as you have the conducive environment, as long as there's no moisture, as long as there's the right temperature, as long as your bags or containers are sealed, just like you will seal your regular fertilizers. If you expose them to the environment, then moisture comes in and then things begin to degrade. So storage is important, just like every other material you are storing. And then the other question was what again?
Are nanofertilizers safe for fauna?
Yeah, it's all about the dose. If you use dose that is compatible to plants in the field, then it should be compatible to the fauna around the plants, to the animals and other organisms around the plant. The problem is once you start overdosing, because these materials are so tiny, you think, oh, it's not enough, let me add more. You know, yeah, it's always tempting to add more because yeah, they look small. If you put, if you weigh a kilogram, if you weigh a gram of nanomaterial on a scale, you will need to put more to get the same 1 gram of a bulk material, just because of the weight alone. And by that, you are tempted, oh, it doesn't look much, let me add more. Then you begin to add, and you are overdosing the system. So once you stay within the boundaries of beneficial effects, then you don't see any effect on the fauna that is unwanted. It's all about the dose.
I'm sorry, Chris, I think I forgot just one last question from Adewale Adeloye. So Adewale says, he's just wondering how effective will the spray of nanofertilizers to finished fertilizers? Is it not better to agree to add this nanoparticle into the fertilizers during manufacturing? So,
yes, if the company agrees to, if they feel it's not disruptive to their process, that would be the best way to go actually. But we have talked to some of them. The question they ask is, hey, what do we do? We already have our plan set up. This is how we run our, you know what, SOP. You have to follow the SOP. Once you incorporate anything else, then it means you have to modify your process. So to avoid modifying your process, if you add it at the end, you can get the same result. I've showed you some examples of what we did at the end of the process to get very effective nanofertilizers. Preferably you add it in the process, but if there's no allowance for that, then you have to do what you have to do at the end of the process.
All right, no, thanks a lot, Prof. Dimka, for such an inspiring and interesting presentation. And in concluding, I would like to thank you again for availing yourself, and also thank our audience, because we started at around, I think, 60 participants. Now we are at 33. I know that this was a long webinar. So I would like to thank you for your patience and also for sitting until this time. And from my side, I would like to say that the take-home message from this presentation is to note that one size does not fit all in terms of the nanofertilizers. It's important when you formulate, you know, why are you nanoformulating your nanofertilizers, and also the type of the soil that you want to apply your nanofertilizers on, and also the type of the plant that you want to work on. So I think I would like to hand over to Samuel so that he can tell us about the next the other webinars that will be coming in this month. Thank you.
So I can stop sharing, right?
Yes, yes, you can.
Okay.
Okay, thank you very much, Lebo. And thank you very much to all our participants. So we are going to send you emails with the outlines of the upcoming activities in terms of the next activities that will be coming through. So just look forward to your emails. I don't know if there's any comment from my colleague from UNECA, Victor, before we close.
Well, thank you very much, I think, for the wonderful presentation. And I think it was interesting to learn new things, especially those of us with a chemistry background and the various ways. I think there is very little excuse for African research institutions to say why they cannot be nanotech in the first place. There's so many ways in which they can actually produce nanomaterials, and I'm sure we should be looking at how do we actually move forward and use all this knowledge that I think foster development. So on my part, and I think on behalf of ECA, we just want to thank everybody who was here, and also our key speaker, as well as my colleague Samuel, for organizing this webinar. And thank you.
Okay, thank you very much. I think we've come to the end of our session. We look forward to seeing you all next week when we have our next session. Thank you, and bye to everyone.
Thank you, Samuel.
Okay, bye.
Thank you. Thank you. Bye.
Talk to you later.
Okay, thanks.
Yeah.